the living date spaces. But this morning I realized that the title of the workshop says local Langlands, and I haven't talked about local Langlands yet. But now I'm going to talk about local Langlands. I would like longer chalk. Ah. So, contrary to Tetsushi's talk, this is about the most, somehow, the easiest non-trivial case of local Langlands, but we still have some subtle things to check. These are the representations of GLN with Iwahori fixed vectors. I've given similar talks before, so I apologize if you've heard this before, but somehow I'm slowly making it precise. Over the years. Lambda is my lattice in Kn, and this is a chain of lattices, so this is just a lift of a flag, complete flag in Kn. So this is just P inverse lambda. Iwahori subgroup is defined as the stabilizer of this chain of lattices.
So lattice means O lattice?
Sorry? Oh, yeah, O lattices, yes, thank you. Just like lambda. So stabilizing means that it fixes all the lattices that you see in the chain. Now, this is a subgroup of U0. U0 was the maximal compact subgroup. So this is not normal subgroup. It's slightly smaller than U0, but it contains U1, the principal congruent subgroup. Now, I've been talking about MU rig. So this is the moduli of level U structures. Now, in this case, level U structure is just choosing a chain of subgroups of G, P torsion of G. So this is of course just K to the N. So you're choosing a flag in this space. Recall that we're working over a rigid space, so this is just an atoll group, right? There's nothing so complicated here. Or I can say I have a chain of isogenies. And so this is going to be multiplication by a uniformizer. This is simply given by taking the quotient of G by these finite subgroups. Now using this form, well, either form will work actually, but G was an atoll torsion sheaf over the rigid space, but this will actually extend to the formal model. So this mu moduli of this over the formal scheme M instead of M rig. Okay. So now these isogenies may not be atoll anymore, of course, and this is a finite flat covering, not Galois. So on each of these finite level Lubin Tate spaces or Rapport zinc spaces, we have Hecke correspondences. M was the Lubin Tate space without the level. The other way around, thank you. This is a double coset algebra. This acts on finite level space by algebraic correspondence. Algebraic correspondence is just a pair of maps like that. I mean, maybe I'll just think of this over rig at this point, because I don't really care about the formal model. Now the cohomology, let K hat be the field of fraction of O hat. We'll use E-token's notation, except that I'll make it clear that we're taking the geometric generic fiber. This is the limit as we go up the tower, which means the level goes higher. And take the limit of the cohomology. This has the action of G times J, and this is smooth. Well, the action of G is being quite obviously smooth. Well, we don't have to take compact support for Lubin Tate spaces. I mean, I'm just loosely referring to Mieda-kun's lectures, that these are nice representations of p-adic groups. I think in general you should take the compact support.
But the component of M rig is infinitely.
Yeah, so you're right. So
and cohomology is just direct sum.
So this is,
It is smooth represented.
so, thank you. Yeah. And the cohomology of the finite level is level U is just the space of U invariants. And on this, I have the action of the Hecke algebra, on which, so now this is a double coset algebra, but I take QL as the coefficient field. So this is a non-commutative ring acting on this space, vector space. Now the geometry. So MU is this joint union of Z isomorphic copies of some complete local ring. And this is finite flat over what we've seen this morning, just the power series ring. So this was, without the level that this ring was formally smooth, it doesn't have any interesting nearby cycles. But now we put the level, now this AU will have bad reduction, and it will have interesting nearby cycles, and that's exactly what we're looking at. So this is, I don't know why. Because complete local rings are strictly Henselian, and complete local O-hat algebras are strictly Henselian. These are just stalks of nearby cycle sheaves at the closed points, the unique closed point for each of the connected components. So I'll concentrate on one of the components. This is a sloppy comment. I mean, I'm sort of pretending that we were just looking at one of the components. This product over Z means that you can have arbitrary central characters. So the ring AU is very explicitly known. This is written in my paper with Taylor. It is not smooth anymore, but it has very simple form like that. Of course, this was known for GL2 over QP by Deline and Rappaport. This is a local ring of X0P at a supersingular point. Now, Xi's are sorry. Thank you. Yes, that was n minus 1. Now we have n. This is what each of the isogeny does on the Lie algebra. Okay? So I have n isogenies of height 1, which compose, the composition is just pi, and that's That's what this equation is saying. So that's not so deep. So the nearby cycle of this kind of ring is known by a different work of Rapport-Zink, much earlier than Rapport-Zink space and T psi 2. So I'll explain that. Now we'll move to the usual scheme setting. So a scheme is called strictly semi-stable of relative dimension n minus 1 if it's Zariski locally étal over this ring. Okay. So you can see that that complete local ring is the completion of this scheme at the origin. And by the comparison theorem of nearby cycles that Miyata-kun explained, we know that we can look at the algebraic nearby cycles of this thing at the origin, and that will be the same as the formal nearby cycle of that ring. That was a comparison theorem that we heard yesterday. So this, in particular, it means that X is regular of dimension n. This is flat over O. And the generic fiber is smooth. I have to introduce some combinatorial notations. So Y is my special fiber. This is going to be union of finitely many irreducible, I mean, it doesn't have to be irreducible, but union of proper smooth components. I index them by 1, 2, ... t. So my special fiber is the union of these proper smooth varieties of dimension n minus 1, and this gives strict normal crossing divisor on X. I want to look at intermediate intersections of these things. They all intersect very nicely. So for each subset of delta with m elements, I intersect them to get yi. This is proper smooth over k of dimension n minus m. AI this is closed immersion. I take the disjoint union of all these stratas of dimension, codimension m, and call it ym. This is going to be a finite morphism. Okay. This is I and, sorry, this is J. Well, first, for the Harris-Taylor-Shimura varieties, you can take t equals n, but in general, even for curves, you can find something like that, and perhaps you want t to be much bigger. Yeah. I denote by QL bracket m the sheaf sitting on y. Sorry, sheaf which is a push forward of the constant sheaf on ym by this finite morphism. This is a sheaf on y. This is constructible constant of rank sorry, constructible. And what does constructible mean? It means that it's constant, it's locally constant on some locally closed subschemes. So this is constant on the locally constant subscheme ys. This is the open strata. Set minus. Okay, so this is because on ys you have s divisors intersecting, and that will be mapped from s choose m different stratas of codimension m, and that will contribute to the rank. Each of these push forward will contribute to the rank. Okay, so it will have somehow bigger rank. Okay, and we have a resolution. Sorry, so I'll try to be quick. So the fact is that I star R M J star QL. This is not the nearby cycles, but it's Galois cohomology, somehow the rational version of the nearby cycles. This is just QL M twisted by minus M, which is kind of nice. And there's a resolution of the constant sheaf coming from the geometry. Which I call, I think this is Rapport zinc notation. Like that. I mean, I don't define these maps. These are defined by alternating sums of the maps coming from the inclusions of smaller strata into bigger strata. So this is just like a simplicial complex that you use when you compute the singular cohomology. So, and the fact that there's a resolution like this is like an inclusion principle. How you have a constant sheaf on something that is normal crossing, and you're saying that this is contained in the somehow the sum of what the sheaves coming from each of the components, except that then you're counting the double point twice, so you're going to exclude the double point once, and then you will get that sheaf. So this is like lambda 1, lambda 2. Okay, so that kind of resolution. This is just reflecting the geometry. So there's a very nice picture going like this way. All the way to Rn minus 1. So Rm psi lambda. Sorry, I've been using QL because I was using lambda for the lattice, which is bad. I think I was using QL until then. I have the reflex, right? Lambda. Was everything okay? Yes, it should be okay. So Rm psi QL is a co-kernel of this twisted by minus n. And because this is the resolution, this is also a kernel of del m plus 1 from minus n. Okay. So this is the how sheaf of nearby cycles look like. This is also constructible, and on each of the open strata, ys bar, because now our nearby cycle sheaf lives over the variety over k bar. This is a constant sheaf with take twist minus m with rank now s minus 1 choose m. Okay. So again, I'm using lambda. This is going to be a problem. With trivial inertia action. So usually nearby cycle comes with the inertia action. This is the kernel of the Galois group of the Galois group of the residue field. So each of these will have trivial inertia action. Now there's another structure. There it is. Which is that R psi lambda, R psi QL, is actually in the category of perverse sheaves. Shifted by n minus 1. So this is a category sitting inside the derived category of QL sheaves over YK bar. But this is a triangulated category. This is an abelian category. And I don't explain what it is, but it's just, let me say it's just a very nice sub-abelian category of this derived category. And on this object, I have the action of IK, the inertia group, and this acts via tame quotient. I said that the inertia will act trivially on each of the Rm psi, the cohomology groups of these complexes, but on the complex itself, it has a non-trivial action. And how do we write that action? I take the generator of ZL1. This is a tame inertia, and I call it T. And N is a log of T. This is a monodromy operator. And this will give a nilpotent action on R psi QL. So whenever I have a nilpotent operator on some object of any abelian category, then we have a filtration. So I heard that in any civilized university around the world, in the second year linear algebra, the Jordan normal form is proven using this monodromy filtration. But is that true? It was not true in Japan, at least, but it's true in London, and perhaps it's true in the States, not in Cambridge. But anyway, so this is something very, very elementary. This is what lies beneath the Jordan normal forms. Okay, whenever you have a nilpotent operator on an object in an abelian category. Now the fact is that the graded pieces of this filtration has a very nice form. Namely, so this is a sum over S, which is bigger than both L0 and minus I, the bigger than the maximum of 0 and minus I. Okay, so QL. So if you look at the cohomology groups, R psi looks like pieces of these bigger things. I mean, these I star, J star, Rm, J star. These are the constant sheaves on the strata. The cohomology of nearby cycles look like pieces. Now, if you work inside category perverse sheaves, then the graded pieces of R psi will be these bigger chunks, nice chunks. Okay. So, in many of the formulations of local Langlands, realization of local Langlands in the cohomology groups of Rapport sync spaces, you look at the cohomology groups or the cohomology sheaves of the nearby cycles. But here I'm sort of proposing to look at the derived category version, which will be somewhat, have a different formulation. Digression is that, so the application is that we have weight spectral sequence. Whenever you have a filtration, I have a spectral sequence. like that. And this is the cohomology of the generic fiber by proper base change, as we learned from Yoichi. And this is, by that description, direct sum of the cohomology of these smaller strata. I mean, I had to take into account the shift and the twist, and QL upper bracket was just push forward from the smaller strata, and that was a finite morphism, which is exact, so you get that. I mean, and this has Frobenius weight J I Bay conjecture. So it degenerates at E2. That was a digression. Anyway, take the stalk. At the origin. Look at the smallest basic stratum. Then we get that, and so this makes sense in the derived category of D, B, C of QL vector space, and it looks like that. But maybe I should remember the inertia action. Then this looks like this big thing shifted by -1 and twisted by -1, minus m minus 1, times what's called sp of m. So I don't have time to go recall the classification of Veidelian representations or the local Galois representations, but M is the unipotent representation which has the form like that. Okay. And now the point is that this part has rank n choose m. So this was why I did this geometry part. So that's the answer, but before we dived into this geometry section, in section 1 this was supposed to be the cohomology of the Lubin-Tate space at the Iwahori level, right? And it had the action of Hecke correspondences, right? But this is just a general theory. I mean, I forgot the Hecke correspondence structure. I just used the geometry, and then the arithmetic geometers tells us what the nearby cycles should look like. So now I want to recover, recover or look at the Hecke correspondence again, now this vector space with rank n choose m should have Hecke action on it, because I isolated this sp of m. All right.
How do you get this expression for this all?
Yes. So if I write this thing, it will look like so the I so the weight minus I think looks like that, and lambda 1 lambda 2 lambda 3 will appear in these weights. So I think S is 2, S is 1, S is 0. I'm writing out this thing. And now the n will look like that. Okay, so you'll agree that this is this times sp3. Right? So I'm saying that this times this tensor sp3 and this tensor sp2 and this tensor sp1. And that's the expression I have over here. So it's just writing out this decomposition. Okay.
We know that n is non-zero for these.
Right. These are isomorphisms, yes. This is n equals 3. All right. Okay, affine Hecke algebras. Hecke modules. I'm not sure how much I should go into this. So the way to understand the Hecke algebra for this is this group, Iwahori subgroup, is the Iwahori-Bruhat decomposition. So G is the union of double cosets indexed by the extended affine Y group. So in this case, this is isomorphic to the semi-direct product of Sn and z to the n. Okay, this is a natural action. So one way to understand Hn is to write out the generators. So this is generated by so these SIs are the double cosets of the of simple reflections. T is looks like that. This normalizes U actually. This element normalizes U and normalizes Sn as well. So T inverse is just the double coset of the inverse of this. This is called Iwahori Matsumoto presentation. That's one way to understand Hn, or I can take another kinds of generators. Like this. The good thing is that these will all commute with each other, so generates abelian subalgebra. This is called Bernstein-Zelevinsky presentation. Now the second presentation tells us that HM tensor Hn minus m will map into what I call parabolic subalgebra. So basically, I will have these and this embedding. Okay, so this generates these, and this generates this one, and I have an embedding like that. So you see that I get all the TIs. I mean, I don't really need all the TIs, but anyway, among the generators, the second set of generators, what's lacking is just SM. Okay, you have the simple reflections from I mean, this is corresponding to the parabolic subgroup of GLN, like that. Okay. So Hn is a Pmn minus m free Pn minus m module of rank n choose m. So as you can imagine, we can realize the parabolic induction on hecamodules. So the representations I'm interested in are Steinberg representations and trivial representations, which has the form so Steinberg is like the sign representation. Ti goes to 1. Si will go to either -1 or q, and T 1. So these are one-dimensional Hn modules obtained as U invariant of Steinberg non-trivial rep of GLN. And if I do the non-normalized induction, so this is, I call this parabolic subgroup Pm n minus n to G if I do the parabolic induction and take the Ivahori invariance, then what I get is so this is defined as induced module from the parabolic subalgebra to the whole of Hecke algebra. It's non-normalized. So if I take sp m and 1 n minus m, that will have rank and choose m. So Steinberg and trivial will give you one-dimensional modules. So if I cancel them, this is just a one-dimensional module, and I induce it from this subalgebra to the whole algebra. And the whole algebra is a free P module of rank n choose m. So this will have rank n choose m. And according to the work of Bernstein and Zelevinsky, it will have two irreducible constituents, which I denote by, well, maybe these are Hecke modules, so I should use rho, maybe. So usually when you do the local Langlands, you make the Galois representations correspond to the irreducible representations. So you call one of these things, for example, I mean, if I have the corresponding thing over GLN, split times Steinberg times ind call it m box plus 1 n minus m or something, and then make this correspond to what we see on the other side. But it turns out that if I compute the Hecke action on these nearby cycles, then the upshot is that R psi QL x what I see as being paired up with sp of m here, this is the full induction. I think I can put the Tate twist on this side. So if you look closely at the Iwahori level looping Tate space and compute the nearby cycles, this and work in the derived category, look at the graded pieces of the perverse sheaves, then what you see is this correspondence. So whenever you have non-tempered things, the definition of local Langlands become a bit subtle. I mean, and for GLN, you don't really care too much because you just pick one of the irreducible constituents and define that this is the local Langlands counterpart. But from geometric point of view, these non-tempered things will come in pairs. And if you take the cohomology groups of this complex, then you will only see one of them. So that's the difference. And this can be proven, computed by using local intersection theory. I mean, I'm going to actually compute what these generators of the Hecke modules do on the looping Tate space geometrically and compute these characters, and this is the answer. I can ask the question, what do you see for Iwahori level rapport zinc spaces for D not equals 1? You still have Iwahori level thing, and you have affine Hecke algebra modules, but you can ask what kind of Galois representations you see, but very little is known about the cohomology of rapport zinc spaces for D not equals to 1. I'll end here.